So I will essentially talk about, and then of course I'll continue with where I left. Physical aspects of general relativity. So I'll begin my lecture today with this. So whenever you're ready, I can start. Yeah, I can start. Right. So I'll begin today's lecture with the physical aspects of general relativity. As I said, that in a curvilinear coordinate system where x mu is arbitrary, like you can think of r theta phi coordinate system, then what do you mean by actual measurement taking place in this coordinate system? So let's start with spherical polar coordinate system. There we have your usual 3-dimension. And let's take one point at position vector r and another point at position vector r plus dr. So in Cartesian coordinate system, this point will have coordinates x, y, z. This point will have coordinates x dx, y dy, and z dz. Now, we are talking about measurements, and we ask ourselves, between these 2 points, what is the physical distance? So here you have a rod. One end point of the rod is at xyz, the other end point is at y plus dy, and we ask ourselves, what is the length of the rod? And because xyz, they have the Euclidean metric, here the metric is Euclidean. That means Pythagoras theorem is valid. We know, therefore, delta L square, Pythagoras theorem tells us that it is delta x square, delta y square, delta z square. It follows from Euclidean geometry, and the distance between infinitesimal thing is, so in particular, dl square, the invariant length. Why is it invariant length? Invariant under what? Under rotation or translation. Whether you are having a coordinate system x, y, z or any rotated coordinate system, the distance between the 2 ends points of the rod is invariant. It is dx square, dy square, dz square. And in Euclidean coordinates, that means Cartesian coordinate system, this distance is well defined. But someone, let's say, doesn't know about Cartesian coordinates. He has simply no idea about Cartesian coordinate system, and he decides that he will use the spherical polar coordinate system r theta phi. In the spherical polar coordinate system, we know the coordinate of this point is r theta phi, and similarly the coordinate of this point is r plus dr, theta plus d theta, and phi plus d phi. If he asks, how do I measure the distance between these 2 points? If he sets, oh, my friend uses dx square plus dy square plus dz square, shall I write it as dr square plus d theta square plus d phi square? It is wrong and is meaningless, because the physical dimension of theta and phi is they are dimensionless. R has the dimension of length, but theta has no dimension. Angles are determined by ratio of 2 lengths. They are dimensionless. These are very basics. Angles, you ask yourself, where did the notion of angle come from? If you delve deep into it, angles are nothing but ratios of distances that can be seen from the circle itself. If you take the circle, then if you take angle this theta, how do you get this angle theta? This is nothing but this divided by this length divided by r, because this is simply r theta. This distance is r theta, which is r. So angles are always ratios related to ratios of distances. So angles are dimensionless, and therefore dr square plus d theta square plus d phi square is a meaningless quantity, and it can't be the distance. Then he says, okay, what do we do? I mean, if I am using r theta phi coordinate system, how do I get the distance? Then he has to know the transformation property between r theta phi and x, y, z. Okay, the transformation property is very simple when he uses the fact that r is square root of x square plus y square plus z square. Similarly, z by r is cos theta. So theta is defined in terms of z divided by, and similarly x is r cos, r sin theta cos phi, and y is r sin theta sin phi. Once he knows the relation between Cartesian coordinates and spherical polar coordinate system, only then he takes his r theta phi coordinates of this point, takes the r theta phi coordinates of the other end of the rod, transforms them back to Cartesian coordinate system, measures the length, or he can say, I don't want to go into the laborious processes. I will use the fact that this can also be written as dr square plus r square d theta square plus r square sin square theta d phi square. I can use also this for the, okay. So basically it is this result which follows from this, that you make a connection between what you do in the Cartesian coordinates system that tells you how, knowing the metric, here the metric coefficient was what? 1, 1, 1. Here the metric, here it is 1, but here is r square, here is r square sin square theta. Knowing the metric and knowing the relation between Euclidean way and the spherical polar coordinate system, you can get the notion of what is being measured. The same thing happens in the Lorentzian metric system in relativity. So now you say that fine, now we transit, okay. So now we transit to 3 plus 1 dimensional space time, so that we get to know what are the physical aspects of general relativity. Now you say the same thing, fine. Now you have here one event, here another event, and if you use a quasi-Minkowski, or rather, so okay, you have used a general curvilinear coordinate system x mu, so that this event is x mu coordinates, where mu is going from 0, 1 to 3, and this is x mu plus dx mu. I want to know what are the actual measured quantities associated with these two coordinates. the given x mu, I have no idea of what do I mean by the physical distance, meaning three-dimensional distance between the two events. I don't know what is the time, actual time, meaning good clocks measuring what time between the two events. Okay. All I know is that in the arbitrary coordinate system, the metric is given by g mu nu, which in general is function of the space-time coordinates. So what is the connection between knowing the metric in this arbitrary curvilinear coordinate system and the measurements that you are performing? After all, physics is all about measurements and its interpretations. Okay, that's the question we are asking. Go back. What did you do in the case of three-dimensional Euclidean space? You essentially made a connection with the Cartesian coordinate system. Why? Because all your measurements that you know in three dimension is based on Euclidean geometry or Pythagoras theorem. Pyramids, or as some people say, even the Vedic altars during the Rigvedic time use the notion of Pythagoras theorem. So Pythagoras theorem was being used in defining right angles, etc. It's not surprising because Euclidean geometry itself came out of actual measurements. Therefore, we have to do a similar exercise when we talk about arbitrary curvilinear coordinate system and relativity. What is a similar exercise? In special relativity, there is no ambiguity as far as measurement is concerned. In fact, the first paper on relativity by Einstein in 1905 on the electrodynamics of moving bodies, or whatever is the title of the paper, it is all about measurement and its interpretation. What do you mean by time measurement? What do you mean by length measurement, where time dilation was derived, where length contraction was derived? It's all about actual measurement and how do the measurements in one inertial frame relate to the other inertial frame, which finally gets summed up in the eta mu nu, the Minkowskian metric. So therefore, you will say that I will by some means have to go to special relativity in order to make sense of what we measure. But here there is a non-trivial problem. Unlike in the case of three-dimensional space, where you had a global Cartesian coordinate system and therefore you could relate the spherical polar coordinate system in terms of Cartesian coordinate system. Here you don't know how to set up global Minkowskian coordinate system. But then, as Einstein realized, no matter what, you can always have small enough region which for small duration time you can set up Minkowskian coordinate system where gravity disappears and special relativity is correct. So therefore, what you will say is the only way to do measurement is here for a small time go to a freely falling frame of reference. And therefore, view these two events in terms of local inertial coordinate system. So this will have the coordinates xi alpha. I am using Weinberg's notation. Weinberg will use in his book xi's as local inertial coordinates and x's as curvilinear coordinate system. So in the local inertial frame, same two events one will have in one of the local inertial frame. As I said in my previous lecture, there are infinite number of local inertial frames, okay, at disposal. So in one of the local inertial frame, this event, let's say, has a coordinate xi alpha, this event has the coordinate xi alpha d xi alpha. Okay. And what does my tensor calculus or differential geometry or what have you completely without any ambiguity tells me? It tells me that in the local inertial frame, the invariant proper distance between that ds indeed is eta alpha beta d psi alpha d psi beta is equal to same, it's same as so around, see remember in the curvilinear coordinate system metric depends upon x. X is the local x coordinates in the curvilinear coordinate system. Okay? All right? So in other words, this measurement is a measurement, actual measurement, which your local inertial frame observer will do, because the d psi alphas are x, y, z coordinates, which are Minkowskian coordinate system. So delta x or dx is the actual spatial length. Delta dy in the x direction, dy is the actual y component distance, and dt, the d psi 0, is the actual time measured in the local inertial frame. So now you say, yeah, those are the times, and what is invariant is this. So this is indeed, this is actually square root of c square dt square minus dx square minus dy square minus dz square, and dt is actually the time measured in the inertial frame's clock. Dx is actual length measured, is no longer a coordinate anymore, is the actual length measured. Dy is the actual length measured. Okay. All right. Now, in this local inertial frame, by definition, all the clocks are synchronized. How they are synchronized? By sending light signals. So those who have gone into the basics of how clocks are synchronized in the inertial frame, the way you synchronize clocks in the inertial frame. Yeah, you please.
There are infinite inertial frames.
Yeah.
I can think of, let's consider Cartesian coordinates.
Huh?
So Cartesian coordinates.
Yes.
So I have infinite number of Cartesian coordinates placed everywhere.
No, wait. When I said one system of Cartesian coordinate system will tell you one Minkowskian frame. That's not what I mean by infinitesimal local inertial frame. So, okay. So let's go step by step. One grid of Cartesian coordinate system. So you have set up a Cartesian coordinate system x, y, z. So therefore you have a cubic grid, and at every point you have clocks. That is your one inertial frame of reference. And by definition I said, what is this inertial frame? That a particle not acted upon by a real force either will be at rest or will be moving with uniform velocity. It's one inertial frame. However, if I am moving with respect to this frame with a velocity, uniform velocity v, which of course I will not say I am moving, I will say I am having a similar coordinate system, this guy is moving in the opposite direction with the minus v, that's also a valid inertial coordinate system. Even if I am not moving, another friend of mine, he is rotated with respect to me, that's also a valid inertial frame of reference. So there are infinity of them. In a given, therefore, even in a given local region, in these two events, in this local region, I'll have infinite number of inertial frames. By the way, each inertial frame is freely falling only. So now your question.
This psi alpha, this is the coordinate I'm measuring
In one inertial frame.
from the origin of
Your frame.
Standard measurement from origin to that point.
Yes.
Now what is d psi alpha?
D psi alpha is so your inertial frame, let's magnify it. So let's say this local inertial frame has the origin, this is my origin. So the spatial component, so this is my psi alpha, this is my psi alpha per d psi alpha, and this will have x component will be d psi 1, y component will be d psi 2, z component will be d psi 3. Is all in the Cartesian coordinate system. So there is no ambiguity. In the Minkowskian coordinate system, there is absolutely no ambiguity. These are the three-dimensional distance actually.
And this d psi itself is measured from the same coordinate which I have measured d psi. Sorry.
Yeah. Same, what?
I have a psi alpha which I have measured from.
Those are all the spatial, that is xi 1, xi 2, xi 3, they are the x, y, z Cartesian coordinate system in your inertial frame. And dx is indeed the separation, that is actual physical length.
In the same frame.
In your inertial frame, right? Okay. Okay. So now we were talking about synchronization of the clock. So in a given inertial frame, so this is one inertial frame, and here there is a clock, here there is a clock, they are all good clocks. How do we know that these two clocks, they are synchronized? The good clocks mean the rate of ticking is identical, but if I measure here the time to be 12 p.m., how do we know that this is also 12 p.m. at the same time? Now this is also very important. At the same time in special relativity is valid only in one inertial frame. The notion of simultaneity, as we know, that's what Einstein for the first time pointed out, the notion of simultaneity is relative. Two events which are simultaneous in one frame of reference are not simultaneous in other frame of references. So therefore the only way to ensure the notion of synchronicity of clocks is you do what? You do this. First, you measure the three-dimensional distance between them, supposing it is L. Okay? And I want to synchronize this clock with this clock. And our agreement is, I have an observer here, I have an observer here, and this observer has already communicated to this observer that I will send a light signal from here exactly at 12 p.m. When you receive the light signal, you synchronize your clock to 12 p.m. plus L by C. We have made this agreement that I will send a light signal at 12 p.m. When you receive this light signal, then set it to 12 p.m. plus L by C, and then at the same time you send me the light signal, and I will verify that my clock recording right that time is 12 plus twice L by C p.m. When we agree on this, we have synchronized our clocks. Okay. So this is the basis of synchronizing clocks in inertial frames. And someone will say that, well, how do we ensure that the C, this light moving in vacuum, light's velocity is not changing? That is the second postulate. Second postulate of special relativity tells under no circumstance the speed of light in vacuum can change. By the way, I would like to make the following modification to the special relativity. Very often students say, oh, what is so special about light? Why light? There is nothing special about light. Therefore, the second postulate must be modified that I can send any signal constituted of zero rest mass particle. Because by definition, all zero rest mass particles have to travel with that number C. I can prove it. Why is it so? By the way, these are not proved normally in textbooks, so there is no harm in proving it. We know that the inertial mass as a function of speed is rest mass divided by square root of 1 minus v square by c square. This equation can also be written as, this is equivalent to m0 is equal to m into square root of 1 minus v square by c square. And therefore, if you put v equal to c, necessarily m0 is 0. So in other words, this proves that any zero rest mass particle moves with speed c. This is the proof. This is all special relativity. I am not doing any general relativity.
So, sir, I have a question. Like, if there is a relative motion between these two clocks, so how do you then define this synchronization of clocks?
No, you can't. So in a given, so in a given frame of reference, in a given inertial frame of reference, the clocks are static. My grid of clocks and measuring rods are static. That's the definition of my one inertial frame of reference.
I mean, we can synchronize clock in only a given inertial frame.
Of course, because that's the whole point of the that paradox. That if agreement between two frames, very often the paradoxes happen because the observer who is moving with respect to this frame will say, well, your clocks are not synchronized. And it's true, because his clocks that are synchronized in his frame, that will not agree, that will say that the clocks here and clocks there are not synchronized in your frame, and that's why you're making wrong measurement.
So this is actually the same, that you cannot have simultaneous events in two different.
Exactly, simultaneity of two events at two different physical location is not universal. Those are the things which Einstein came out. Einstein did physical argument. Of course, all that in Minkowski notation are trivialized. I will say that, by the way. I mean, particle physicists only use Minkowskian coordinate system. I'll do all that. I'll do that. I must not jump the gun because it can be very confusing otherwise. But first, let me look at the physics point of view. So I hope synchronization in inertial frame of reference is clear. Now we'll come to your question, that how do we synchronize clocks in curvilinear coordinate system? Infinitesimal clocks, I can use these arguments. Okay. But is there a notion of going to non-infinitesimal? Why infinitesimal? Because infinitesimal, you'll say that yes, for a small time I can use the same argument. Because in an infinitesimal system, I can choose the local coordinate system, and therefore the speed of light is indeed c. What happens to general distance? First of all, in arbitrary coordinate system, you don't even need synchronization. That's the whole idea. You can have any t coordinate, you can have any space coordinate, doesn't matter, the physics is independent. So you don't need synchronization in arbitrary coordinate system. But then you will ask the question, if you don't need, what is the physical measurement you are doing? That physical measurement you do, you have to go back to a local inertial frame. I'll illustrate by giving the example of the measurement of time in curvilinear coordinate system. That will clarify. But I should not, so, okay. So the bottom line to your question is that if the clocks are infinitesimally close by in curvilinear coordinate system, I can use the same technique of synchronization, but at a broader level, because in general relativity everything is covariant under coordinate transformation, in particular ds square is invariant under coordinate transformation, you don't need synchronization. You don't need synchronization, your x mu coordinates are just labels. They're just labels. You can label them by any thing you wish, as long as they are continuous variables, because the derivative you should be able to take. So they are just labels. So synchronization is not important at all. But measurements are something that is very relevant to physics, and what you measure you have to fall back to inertial coordinate system. Just like when you did the measurement, the fact that this is also physical, that this is what you measure by length, came from the fact that Euclidean, in Euclidean metric, this is what the physical distance is. So that's very important. So I'll talk about two examples where we make a correspondence with measurement and curvilinear coordinate system. I'll give you two examples. Okay, one is the gravitational time dilation or gravitational redshift. Anuj has done it in a particular way as to why do clocks go slower in strong gravity compared to weak gravity. Okay, there is one way I remember Anuj has shown. I will show using the fact that we had already proved that G00, when there are weak fields, G00 is 1 plus 2 phi by c square, where phi is the Newtonian potential. So I will use this kind of argument to show what is the actual time. All right, that is one case I will show. And some of you are doing research in cosmology. I'll show that in cosmology, when we say, the angle between the radio lobes of a radio galaxy is this, but what is the physical angle? How do they correlate it? That I will make a correspondence. All right, so that we understand that even in curvilinear coordinate system, when the metric is not 1 minus 1 minus 1 minus 1, what do we mean by measurement? Okay, yeah. So let me first talk about gravitational time dilation. So that will give us some understanding of making measurements in curvilinear coordinate system. Normally these are not explained in detail, but it is understood. I mean, it's not that they are not there. You have to be very careful in reading in between the lines when you read Weinberg or Landau-Lifshitz. In fact, Weinberg, I think, makes a mistake in his first edition regarding gravitational time dilation. He has made a mistake in his book, first edition at least. So what I am going to say is related to Pound-Rebka experiment, which showed that indeed what Einstein was telling about gravitational redshift, they actually did the measurement and showed it. So what I am saying is very simple. Supposing I have a weak gravitating source, you can think of Earth, and on the surface there is a clock ticking, and then at some height there's another clock, but these are very relevant for GPS because clock synchronization is very important. Here there's a clock. And we want to know the two clocks, if events are happening, what do they translate as far as the clock here and the clock here. All right? Now, let's say we want to know the clock ticking here and clock ticking here, what are the correspondences? That is what we are interested in. Knowing the fact that the G00 for our system, G00 of x mu, we have already shown in the weak field approximation is 1 plus 2 phi of x mu. And because we are talking about static system, there is no time dependence, we might as well say just x vector, because in Newtonian case there is no time dependence. This we had already shown, taking the action of a particle. So this is my G00 metric, And let's say here the clock is ticking, and this is the coordinate time of the clock. So the clock is here using x mu coordinate system, and these are the coordinate thing, and it says that supposing two events happen at the same spatial point at two different coordinate time. Okay? Okay? So therefore, two events happen at this clock. The hand ticks, one tick at coordinate time t1, then another tick at coordinate time t2. So two events happen. So t1, but the position is fixed. So t1 at position x, and at t1 plus delta t1, the other tick happening at t1, the same position. Okay? All right? So therefore, what is the invariant proper distance between the two events? So one event t1 at x, t1 plus delta t1 at x. So therefore, delta s square at this clock. What is delta s square at this clock? Delta s square by definition is g mu nu delta x mu delta x nu by definition. Okay? By definition, it is this. But it is happening at the same position. So delta x is 0, because the clock in this curvilinear coordinate system, the clock is static, x is same. So this is simply g00 of x c square delta t1 square. Agreed? Yeah, Snehil. The clock, so the clock is fixed at my x mu coordinates. So the x mu is curvilinear, and the ticking is infinitesimal. Delta t1 is tiny. Agreed? Everyone agrees? And let's say the clock position is x1, because here it's a different clock position is x1. So g0 is x1. The clock is in its coordinate system. It's like, by the way, these x1 and t are not Minkowskian coordinate system. It's an arbitrary coordinate system. So delta x square is this. Okay. Therefore, you will say, what is the physical time? This is only the invariant time, g0 is x1 c square delta t1 square. But you will ask, is it what clocks measure? You will say, okay, inertial coordinate system. Remember, our interpretation of measurement is based on inertial coordinate system. Agreed? So you will say that during this time when the event was happening, t1 x1, t1 plus delta t1 x1, here supposing I had chosen an inertial frame of reference, which when the events happened, it was at rest with respect to the clock. That means it was co-moving. So in that, when these two events happen, remember, that's why Snehil's question is important. Delta t1 is tiny. So during the tiny delta t1, let us look at the two events from an inertial frame of reference with respect to whom the clock was not moving during delta t1. So therefore, the spatial the proper distance between the two events in the xi a system, which is Minkowskian coordinate system, the same event delta s square, where delta s square is invariant, will be delta alpha beta, delta xi alpha, delta xi beta. But in this frame, the clock is not moving. And therefore, this is same as eta 0 0 delta xi 0, delta xi 0. Agreed? Yeah. But eta 0, 0 is plus 1. So this is same as delta xi 0 square. Okay. Everyone agrees? And delta xi 0 square by definition is c square in the proper time, that is the actual time measured by the inertial observer clock. Let me call it delta tau square. Okay. So we know that the real measured time by inertial observer between the two ticks of the clock, provided that delta t1 is infinitesimal, satisfies the relation c square delta tau square is same as g00 x1 c square delta t1 square. Agreed? So these two being equal, I get the result that delta tau is nothing but square root of g00 at x1 delta t1, where this equal c square get cancelled, delta tau is this. All right. And what is the interpretation? This is the time interval as measured by an inertial observer who was co-moving with this clock. That means with respect to a local inertial observer for whom the clock is at rest, the actual time elapsed between the two events is this. And G00 is this, so therefore this is same as square root of 1 plus 2 phi of x1 by c square delta t1. So let's take a pause and interpret what. So this is what I mean when you make a correspondence with measurement in general relativity, you have to do a lot of deep thinking. I mean, I'm not saying it was done already. There's a whole book by C.M. Will on measurements in general relativity. So people who are in this field, they know what they are doing, but therefore it is very important that we understand what is happening. So we have chosen a coordinate system x mu. In that coordinate system g00, when the gravity is weak, we have established g0 is 1 plus 2 phi x by c square, and then we are saying that if delta t1 coordinate time elapses in the clock, then the actual physical time that has elapsed, meaning what? The physical time that has elapsed in a co-moving local inertial observer is related to delta t1 in this manner. Okay. Yeah. Ask.
That delta t1 time is actually the ticking of the clock, or
No, it is the coordinate time.
that has no physical significance?
So we don't have any physical significance because that is not the invariant time, it's the coordinate time.
So how do we actually
Wait. Well, we are going to it. We are going to it. Now, there are many ways of doing it. First, I will tell you the theoretical way, but you will say that, no, I am not convinced by it. Then you will say, then I will use light ray, and that will make a correspondence gravitational redshift. So let's go very. So there is a clock here, and the relation between the ticking coordinate time delta t and the actual time elapsed as measured by a inertial observer, this is the relation. X1, by the way, is arbitrary. X1, the clock could have been anywhere. Okay. Now, I'll give the one theoretical reasoning, but some people might not be convinced. This is so important, I am slowly saying it with the danger that my course has become slow, but we'll take extra lectures and cover it up. Because I wanted to finish Riemann tensor today, because TP is going to do Riemann tensor tomorrow. But anyway, probably in the afternoon we can cover a little bit. But these are important. We have to talk about it. These are which cannot be answered from ChatGPT. So it's better that we do it here. Okay. Now, the clock could have been anywhere. So supposing I have a clock at so far away, so very far away, that phi is 0. Why? Because as Anuj that day pointed out, one of the great coincidence, I mean that's the reason why Newtonian gravity works. One of the great coincidence is that if you have a spherically symmetric mass distribution having mass m, then the exact solution, which is the Schwarzschild solution, is 1 minus 2gm by c square r at a radial coordinate r, and it so happens that the Newtonian potential for this, phi of r, is also minus gm by r. It's a coincidence, then that need not have happened. But it turns out that this one is an exact result for a spherically symmetric distribution. For a spherical symmetric distribution, actually G0x is not approximately equal, is equal to 1 plus 2 Newtonian potential by c square. Again, what is mass and all, that's a separate question. Which mass are you using? That's where ADM mass, and I don't want to go into those details. Those are also subtleties. And the fact of the matter is, the Newtonian potential or the exact Schwarzschild G0 isometric, as r tending to 0, r tends to 0, this term goes to 0. So G00 is 1 at r tending to infinity for a Schwarzschild metric, and so is the Newtonian potential. At r is infinity, Newtonian potential is 0. So therefore, if you had taken the particular clock at infinity, your delta tau would have been delta t1 exactly. So a clock, and these are identical clocks, the ticking is the coordinate time. So these clocks, if their coordinate time ticking agreed with each other, a clock at infinity, delta t1 is exactly the physically measured time delta tau. Agreed? So there is another way of saying is, so someone will ask, what is delta t1? Delta t1 is the real or proper time. That's the best way. That's why is the proper time, which is the physical time, proper or physical time as measured by identical clocks of the kind of this clock, by identical clocks at spatial infinity, by inertial observer, at spatial infinity. That I argued, because this x1 could have been anything, and for x1 tending to infinity, phi is 0. Okay? Now that's very interesting. So let's now put in the values. So this is 1 minus 2 gm by c square if the clock is in your curvilinear coordinate system at r1, delta t1. So which is bigger? When r1 is not infinity, you can see that because of the minus sign, you see for r1 not equal to infinity, of course infinity doesn't exist in mathematics, so I am being cavalier, for r1 not equal to infinity, delta tau is less than delta t1. Okay? So therefore, you have the statement that clocks in gravitational field, they tick at a slower rate. Why? The same two events, the same two ticking of the events, the inertial observer will say that the time elapsed is delta t1. But the observer at the clock, local inertial observer, he will say, no, the time elapsed is smaller, so the clock is ticking slower. Okay? So that's the reason why in textbooks you have the statement that clocks in gravitational field click at a slower rate. So this statement implies clocks in gravitational field tick at a slower rate. The other way of doing it, someone will say, oh, we are comparing an observer at infinity, but who can compare time with an observer at infinity? There's another way. And that's the Pound-Ripka experiment. What you do is that you send at every tick, you send a light beam. So when it tick T1, you send a light beam to the clock here. Another light beam at clock here. Okay? You can prove, because remember, the clocks are all ticking. If it is delta T1 here, the two light beams, if they're separated by delta T1 here, it will arrive also at delta T1, coordinate time delta T1 separation. But what is the physical length? Physical length will be, here it was this, here it will be delta S square will be G00 at x2 c square delta T1 square, and hence this implies that delta tau, so I'll call some label. So delta tau 1 here and delta tau 2 will be square root of 00 at x2 multiplied by, I am not going through the whole lot of thing because x1 was arbitrary. The two light signals, here the actual proper time difference between it is delta tau 1. When it arrives here, the actual time difference for an observer here, actual time difference meaning local inertial frame, is delta tau 2, it is given by this, and therefore this is equal to 1 minus 2 gm by c square r2. This is delta tau 2. What is that? Yeah, this is delta t2 and this delta t2. This is delta t1 because the same delta t1, because the same light being coming here. The field, gravitational field is not changing. So coordinate time delta t1 will be the same. Okay? But now you say, okay, what are the measured quantity? Tau 1 is all that, but supposing I am sending a light, there is a crest of the wave, this T1 corresponds, so there is a light wave coming, and this is at T1, this is at T1 plus delta T1. So therefore, this is the C into delta T1 will be what? It is the wavelength of the light emitted. So therefore, C into, so emitted wavelength is C into delta T1. C into delta, not proper time, delta T1, which is 1 minus 2 gm by c square r1 delta t1. While observed wavelength, when it comes here, the observed wavelength, lambda observed, is c into delta tau 2. So c 1 minus 2 gm by c square r delta t1. And therefore, lambda observed by lambda emitted is delta t1 cancels, c cancels, square root of 1 minus 2 gm by c square r2 by agreed. Okay. Now, so light which was sent from the top had the wavelength lambda observed, but the wavelength that is observed at the surface of the earth is given by this. Question is it greater than 1 or less than 1? R2 is smaller. Huh? R2 is smaller because R2 is near to the less than 1. Okay. So, what does it mean? That when the light is coming from top to bottom, its wavelength shrinks or the frequency increases. And this was verified using a Mossbauer source, because Mossbauer source, you know that Mossbauer source, when a nucleus embedded in a crystal emits a gamma photon, the gamma photon's wavelength is exactly the separation between the excited level of the nucleus and the ground state. There is no recoil. Okay? That was a graduate student, Mossbauer, discovered this effect in while doing PhD, because the entire crystal takes away momentum. I don't want to go into it's a fascinating thing. Mossbauer effect is fascinating, and this was observed. It's called Pound-Repka experiment, which confirmed that falling photons, their frequency increases or wavelength decreases, or the reverse. When you send a laser beam, a Mossbauer beam, gamma ray beam up there, then the wavelength gets stretched. This is the gravitational blue shift and gravitational red shift. Okay.
So why does delta tau 2 is equal to, I mean, that under square root of g times delta t1 there? That is
What? No. It is delta tau 2 is square root of g00 x2 into delta t1. The general expression is here. And since x1 was arbitrary, first I did for x1, and the same formula can be expressed in x2.
my problem is why the delta t1
Is same. Why is the delta t1 same? Because your coordinate system has been chosen such a way that when there is another way of doing it, that's a better way of doing it. I'll tell you that also. The coordinates have been chosen such a way that if clocks are ticking at t, delta t, 2 delta t here, the clocks are also ticking at t, delta t, 2 delta t here. That means there's a global coordinate time coordinate defined all over. For example, your Schwarzschild metric, the metric coefficient don't depend upon time. So all the things happen, there's a global time coordinate defined everywhere. In other words, there's a better way. I haven't done the killing vector, so I'm not. There's a killing vector, time-like killing vector. So if light starts at t, coordinate time t, and arrives at another point at coordinate time t plus delta t, then you can show that whenever there's a killing vector, if the light starts at time t prime, it will arrive at the same position at t prime plus the same delta t. You can see it from geodesic also. All right, so I'll erase this part of the blackboard. Here Weinberg, don't see Weinberg's derivation, he does it in the very early, he makes a mistake. I don't know how a guy like Weinberg made a mistake in the first edition of his book. Of course, time is always a confusing thing. You can, unless you are careful, you can get confused thoroughly. Now, before I give the example of how you do measurement in cosmology, I'll point out two very important things, which is extremely important. So, they should be pointed out. Very often people ask, okay, in special relativity, light travels with speed c. Light or any zero rest mass particle. As I said, any zero rest mass particle travels with speed c. Okay? So therefore, you might ask that in curvilinear coordinate system, when space-time is curved, does light travel with speed c? Very often students ask me that, okay, in special relativity you told me that always light or zero rest mass particles, they travel with speed c in inertial frame. What about curvilinear coordinate system? Curvilinear coordinate system, velocity is coordinate dependent. What is normal velocity in special relativity? Velocity is a 4 velocity in special relativity. In special relativity, you have a notion of 4 velocity. 4 velocity denoted very often as u alpha, by definition is your Minkowski coordinate system dx alpha by the proper time d tau. What is d tau? D tau is 1 over c ds, which is nothing but 1 over c square root of eta alpha beta dx alpha dx beta. I am using the signature plus minus 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 minus, otherwise it will be negative of that. Okay, and dx alpha by d tau is the 4 velocity. Okay. And 4 velocity in special relativity is a measured quantity. Why is it a measured quantity? As I said, dx alpha is infinitesimal Minkowskian coordinate system that in your inertial frame, that's what you measure. Okay, we just now, Fairoz asked, what is this dx, what is this dy? They are actual measured quantity. So 4 velocity in special relativity is a measured quantity, measurable quantity. Now you go make a transition to general relativity. I did not ever make this statement. How do you go if you know physics in special relativity, you want to do physics in arbitrary curvilinear coordinate system? What do you do? What is this prescription? Prescription is, it's called the principle of general covariance, dealt in detail, very beautifully done in Weinberg's book. The prescription is very simple. Wherever you have eta mu nu, replace by g mu nu. Wherever you have ordinary partial derivative, replaced by covariant derivative. If you can do that, whatever you have learnt in special relativity, whatever laws you have formulated in special relativity, just do that, you have the effect of gravity on that system. So Maxwell's equation in special relativity is what? It's simply del f mu nu by del x nu is proportional, that 4 pi by c, I always forget, it's j mu, proportional to j mu. In curved space-time, if you want to know what you are doing, so mu nu, they are no longer special relativity indices, they are general curvilinear coordinate system, except the formula will be g mu nu semicolon nu. We have already seen what are covariant derivative. We have introduced this partial derivative becomes semicolon and will be proportional to g mu. That's all. And you can do electrodynamics in curved space-time without making any mistake. Provided, of course, I'm assuming these electromagnetic fields are test fields. They are not disturbing the geometry themselves. So the prescription is, if you know your physics in special relativity and you want to study what happens in arbitrary curvilinear coordinate system or arbitrary space-time geometry, all you have to do is wherever you have eta alpha beta, replace it by g mu nu. Wherever you have ordinary partial derivative, replace it by covariant derivatives. Okay. So therefore, when you go to general relativity, you ask, what is the notion of 4 velocity? Four velocity is again defined, just now we said, all you have to do is wherever there was eta alpha beta, make it g mu nu and so on. Again you have u mu, and u mu is dx mu by d tau, where now d tau is 1 over c g sigma tau dx sigma dx tau. I am assuming Einstein summation convention system. Okay. But now you see 4 velocity. So this, by the way, I should have mentioned, this is well defined from measurement point of view. Well defined from measurement point of view. Point of view. But dx mu by d tau, it has no meaning in as far as measurement. Your x mu's are arbitrary coordinate system. They will not even have the dimension of velocity. For example, if I take spherical polar coordinate system, your u theta will be d theta by d tau. D tau will have the proper dimension, but d theta by d tau doesn't have the dimension of velocity. So in general relativity, your 4 velocity u mu dx mu by d tau has no physical significance as far as measurement is concerned. And now you are going to ask, so now light. How do light move, therefore, in general relativity? Knowing special relativity, can we say anything about motion of light in arbitrary curvilinear system, arbitrary space-time geometry? The answer is yes. Why? Because ds is invariant. ds, so if a light is moving from this event E1 to another event E2. So let's say you have a zero rest mass particle, which is all zero rest mass particles move with speed c in special relativity. Supposing a zero rest mass particle is going through such that there is a detector here, it sees an event here, and it carries on, and another detector sees here that zero rest mass will passes, and let's say the coordinate of this event is x mu, the coordinate of this event is x mu plus dx mu. In special relativity, I will say that these two events are connected by what? ds square is c eta alpha beta xi alpha d xi beta, which is same as c square dt square minus dr dot dr, same thing. And if it is zero-rest mass particle, what will be this? 0. Which is same as dr by dt being magnitude being c. But ds square is invariant. So it's same as g mu nu dx mu dx nu. In other words, what we arrived this using our reasoning, what we'll get is that g mu dx nu is 0 for any two events connected by a zero-rest mass particle. And that's why null rays in general relativity, null rays, those trajectories call that x mu of lambda, those trajectory where lambda is a parameter, real parameter, tell me where null trajectories are those trajectories for which g mu nu dx mu by d lambda dx nu by d lambda is 0, because g mu nu dx nu for null rays is 0. It purely follows from the invariance of the proper distance and local inertial frame. The fact that here if you had chosen a local inertial frame, you would have seen that ds square would have been 0. And therefore, in arbitrary coordinate system, g mu nu dx nu is 0. Some books state it wrongly. They say that you have to make an assumption, that it's an assumption that null rays satisfy that condition. It's not an assumption. It follows from local inertial frame hypothesis and special relativity. Okay. The other thing is the causal structure. Okay. So
here again, the free velocity of light, what happens to that?
no, as I said, that notion of velocity is ill-defined in general coordinate system. But yeah, 3 velocities is c, because this can be also recast as c. Then you can't say about velocity anymore. Velocities don't have physical meaning. Because coordinate velocity dx mu by d lambda, no physical meaning. It doesn't have any connection with measurement. All we can say is when null rays or light in vacuum moves, it moves in such a way that this is 0. That's all we can say. So you say that yes, even in curved space-time, light travels in such a way that this is 0. Now whether you can interpret it as traveling with speed c, that's a matter of interpretation. Okay. All right. So now that I am talking about null rays, now we talk about which are the events which are causally connected with each other. This is very important. This is something which is again will not be covered in general textbook, maybe in the philosophy textbook. Cause and effect plays a very important role in everything other than mathematics. This statement you will not find anywhere. This is something is very foundational. Mathematics is one discipline where cause and effect play no relation. You don't see cause and effect in mathematics. You say that Pythagoras' theorem follows from the 5 Euclidean postulate, but where is cause and effect? But science and anything that deals with events, they have to respect the principle of causality. Even economics, as anyone who has done a introductory course in economics know that if the demand of some goods increases, price will go up. So cause is demand of goods increasing and the effect is price of the object goes up. So anything that deals with events satisfy the cause and effect, that things happen because of causes. Even quantum mechanics, if you make a measurement, things will happen, things will change. Hamiltonian causes the state of a system to evolve according to the Schrodinger equation. Cause and effect is central to science in general. Biological system, yeah, you don't give food to microorganisms, they will eventually die. But if you give abundant food, they will multiply and grow profusely. That's the reason why tropical regions like India, etc., growing food or growing trees is easy compared to Siberia. That's why, again, I don't want to, that's why Russia suffered food problem during the 1989, the glasnost and perestroika. Oh, I must not get digressed into different things. Yeah, okay. So cause and effect is central. But then you can ask that here I am, what all things can I causally influence, or what are the things I have been affected causally? In special relativity, you draw the light cone. You say, here is, I am here and I am moving past to present. My world line is going, this is my t-axis, this is my space axis. Okay. At this point of time, all the things which could have been affected are all within this light cone. I am assuming a unit system where c has a value 1. So that light travels in this cone, this is called the light cone. If you choose two-dimensional x and y, it will look like a cone, but of course it's three-dimensional. So anything within this could have affected me. Anything outside the light cone couldn't have affected me now. It can in the future, but now it can. Why? Because in order for effect meaning what? Causal effect meaning what? Anything which carries energy and momentum, only those can affect me. Anything that is not carrying energy and momentum, they can't affect me. If I want to affect that remote, from here I have to throw a chalk so that it hits, transfers the momentum and energy to that. And anything that has energy and momentum, they are limited by this relation. So therefore, either they travel with speed less than c, then they will be having trajectory within the light cone, or if they are moving with c, they will be moving along the surface of the cone. What about an event here? Can it affect me now? No, it can't, but eventually the light ray will affect me in the future, and it can affect me in the future. But today, all the things that has happened within the light cone, only those could have causally affected me. When we talk about cosmology, these are the inflation cosmology grew out of such arguments. If we have time, we will talk about it. And what all things today I can affect in future, all the things in my future light cone. I can't affect anything here, because to send a signal, if anything that goes out of the light cone, it necessarily has to move faster than the speed of light. In special relativity, therefore, we understood the causal structure, what can be affected by us, which all things have affected us. We know in special relativity the causal structure. Someone will come and say, oh, but now we are in general relativity. In general relativity, how can you build your causal structure? The coordinate systems are all curved. The answer is no. The equivalence principle tells us this is invariant. ds square is invariant, and therefore particle having mass non-zero, they will necessarily move in trajectory. So for particles m0 non-zero, of course we know they can't be negative mass. When I say non-zero, they are positive. We know that g mu nu dx nu in my signature plus minus minus necessarily has to be greater than 0. How do we know that? Very simple, again equivalence principle. So null rays I have talked about, null particles we have already talked about. Now we are talking about particles with rest mass non-zero, or strictly speaking greater than 0. So if a particle is moving along a trajectory labeled by the real number lambda, so x mu of lambda, then particle when it crosses this point to another point at x mu plus dx mu, the corresponding ds square is g mu nu dx mu dx nu, and I will now prove that if the particle's rest mass is greater than 0, this will be greater than 0. Why? Because in the local inertial frame viewing these two events, it will be c square dt square dr dot dr. So if I take c square dt square common, I will get 1 minus 1 over c square dr by dt dot dr by dt, which is v square, velocity square. And for particle with rest mass positive, v square by c square is less than 1. So 1 minus v square by c square is positive, and therefore this is greater than 0. And ds square is invariant. So therefore we have proved that for this g mu nu dx mu by d lambda dx nu by d lambda is positive. Okay? So all causally connected, because as I said, effect can be created by cause which supply energy and momentum. That is the only way cause and effect relations are there. If I want to open the door from here without having an electronic device, I have to sufficiently throw a heavy thing to the door so that my momentum opens the door for a brief instant. So momentum energy has to be transferred, and they are limited by speed of light, and therefore locally only those things are connected causally which are causally connected region. So x mu and x mu plus dx mu are causally connected, means they can influence each other if and only if g mu nu, in my signature I am using the signature minus minus. So that means in the local inertial frame, eta 0 0 is positive, eta 1 1, eta 2 2, eta 3 3 are negative. Greater than or equal to 0. So two events, x mu and x mu plus dx mu, are causally connected events. Events at are causally connected if and only if g mu nu x dx nu is greater than or equal to 0. Equal to 0, they will be connected by light, but they can be connected even by slowly moving particle. These are important. That's how you actually figured out that the quasars are due to supermassive black holes, because the fluctuation in the X-rays that you see are very short. When you have a blazars, the gamma rays and X-rays fluctuate over time scale of hours. That means the regions that are emitting, they must be very small, because light travel time, causality connection tells me they must be very small. If it is very big, the light travel time will be bigger. That's how you infer the presence of black holes. Right. All events for which g mu nu, dx nu is less than 0 are causally separated. They cannot be influencing each other. So I will not write it down, it is obvious. So those events which are for which g mu nu, dx nu is less than 0, they are not causally connected, unless there are tachyons. If Sudarshan's tachyons exist, then of course that's a separate ball game altogether. Okay. Now I will tell you, because this is so important, because those who are doing cosmology, how do people, astronomers, things are happening far away and they say so many things about the angular length, diameter and all that. How do they do it? That's an example of how what we do, how general relativity is linked with measurement. That's the thing I will talk about. And but Riemann curvature tensor, I should tell something about Riemann curvature tensor also, because otherwise there will be a problem between TP's lecture tomorrow and so I will take brief time to cover the cosmology part. So the fact of the matter is, as shown by George Lemaitre and Friedman and Robertson Walker, etc., if your universe at some scale is having matter distribution which is homogeneous and isotropic, then you can choose coordinate system which are called Robertson Walker coordinate system, r, theta, phi, such that for observers with constant r, theta, phi, the universe will look isotropic and homogeneous. In such a coordinate system, the line element describing the geometric separation between two events is given by c square dt square minus square of the scale factor that gives the expansion of the universe the physical significance of the coordinates. Those who are interested in the same volume in which Mukunda's article is there on differential geometry, I have an article called Cosmological Constant Tutorials. There I have explained all these using numerical problems. So this is called the Robertson-Walker line element, and when you put them in Einstein equation, you get equations which are called Friedman, George Lemaitre equations. Anyway, but now you say, okay, this is the line element. Now what is the physical significance? What are the r, theta, phi coordinates? Observers, they are called in old cosmology books, they are called cosmic observers. Cosmic observers are those observers for which r, theta, phi are constant, and they carry clocks with them. So what are the actual physical time that elapse? Physical time that elapses ds. So the clocks the cosmic observers carry, cosmic observers r, theta, phi, they are constant. So if two events happen, what is the actual proper time cosmic observer will measure? ds square will be c square dt square, where dr, d theta, d phi will be 0. So the interpretation for that time t, it is the proper time as measured by the clocks of cosmic observer. I hope this becomes clear. You have to therefore know what is the physical interpretation of t. It turns out that because the observer, cosmic observer, by definition are r, theta, phi coordinates constant. So when they are carrying the clock, because ds square then becomes c square dt square, and ds square is the proper time. We have been doing it. ds square by c square is the square of the proper time. So therefore, the interpretation of the time t is a coordinate time in Robertson-Walker coordinate system. Also, it is the proper time as measured by a cosmic observer, because by definition, cosmic observers are those for which r, theta, phi are constant, and also the fact that cosmic observers are those for whom the universe appears homogeneous and isotropic. If I have been moving with respect to a cosmic observer, universe will not appear to me homogeneous or isotropic, because I am moving in that direction, the density of galaxies in the forward direction will appear more than the density of galaxies in the backward direction. Now, so I have explained what is the physical meaning of this time t. Now, supposing in this coordinate system there is a source which is extended very far away, there is a source which is extended. For example, radio galaxies. Those who have seen the radio image of a radio galaxy will see that something is happening around supermassive black hole. There are radio jets, and for the classic radio doubles, there's a radio blob here, and you can ask, you can ask the question, what is the physical distance between the two radio blob? But this is all in curved space-time. How am I going to measure the physical blob distance? These are all curved space-time. So the way you do it is that supposing your radio galaxy, the radio blobs, this direction is normal, this is normal to your line of sight. Here is the observer. He has set up the r theta phi coordinate system. So the source radial coordinate is, let's say, r1. Okay, and it sends what you are seeing is today at the present age of the universe T0. You are seeing the light coming. The actual light signals that started from here was at time t1. Okay, and let's say we can always choose a isotropic system. So I can choose this plane to be theta equal to pi by 2 plane. Okay. It's up to me. You say isotropic system. So I can choose my coordinate system so that these two radio blobs these lines are in theta equal to pi by 2 plane. Okay. If theta equal to pi by 2 plane, then the light signal is being sent from here at time t1 and also from time t1. Let's therefore calculate what is ds square. I'll assume that this angular separation, the angular separation is very tiny actually. So this is d theta, d phi. But remember, theta is same, r1 is same. This blob is also at r1, this blob is r1. So what is ds square? ds square becomes, and they are being sent at same time t1, dt is 0. I'll get minus a square t1, because the light is being sent at time t1, a square at time t1. This is 0. Theta is pi by 2 is 0. So I have r square. Theta is pi by 2, sine square pi by 2 is 1, d phi square. And this is the angular separation, d phi square. You say, this is a negative sign. Why is a negative sign? Because this space-like separation is a space-like separation. They cannot be causally connected, negative. So the two blobs cannot be causally connected. But we are not interested right now about causal connection. We are talking about the length, physical length. So the physical length, actual physical length, dl, therefore, this actual measurable length is square root of minus ds square. But this if you had a local inertial frame freely falling, that's what he would have observed. Always go to the local inertial frame. That's what he would have observed. The two blobs, same time, and he would have got this part as the length, and you have square root. So therefore, you will get a of t1 r d phi. r1, because this is at r1. In other words, for a radio astronomer, all he has to measure is the angular separation between this blob and this blob, which is d phi. He knows d phi. And if he has a notion of at1 and r1, he measures the length. Okay. Agreed? So someone will ask, how do I measure at1 and r1? Okay. It turns out, I don't know whether we will do it, it turns out if light was emitted at time t1, that time the scale of the universe was at1, and present day universe scale, universe expanding, at today is more than at1. You can show at naught by at1. I will not derive it, probably the cosmology tutorials. Who will do the cosmology tutorials? Let's see. So this object is called, you can show this is related to redshift 1 plus z. So if your optical astronomer has measured the redshift, the radio galaxy is a optical galaxy from which radio jets are coming out, and optical galaxy from the emission lines, etc., you can measure the redshift. So if you know the redshift z, then at naught by at1 is known. So this can also be written as the real physical length, which is called the angular diameter. This is sometimes referred to as angular diameter. Physical length L is nothing but a of t naught into radial coordinate of the galaxy into d phi divided by 1 plus z. Okay. Okay. And who will give me at naught r1 by 1 plus z? This redshift I can measure using the emission lines from the galaxy. Who will give me at naught into r1? If there is a time, we will derive the luminosity distance. If we know the radiation coming from that, then I can measure the luminosity distance, and at naught into r1 is related to luminosity distance. The correct relation is luminosity distance is for a source at redshift z is at naught into r1 into 1 plus z. So that's how cosmology, which is theoretical, makes a confrontation with the observation, and this is the subject of observational cosmology. All right. I hope I have told you how to relate curvilinear coordinate system and measurement. Every time we have to fall back to what is being seen in local inertial coordinate system. Even that, this is the physical length, comes from local inertial frame, because if you sit in a local inertial frame at same t1, ds square, same t1 will be minus, if the two things in the x direction will be exactly equal to minus square root minus dx square. So therefore, that's the length. Okay, now curvature tensor, that's very important. So I'll take some extra time to talk about curvature tensor. Otherwise, what will happen is you will not make a connection when TP talks about tomorrow the Cartan equation, because the second Cartan equation will have Riemann curvature tensor. So a large part of today's lecture was about physical aspects of general relativity, which is not generally in detail covered in books, although it is implicitly assumed that readers understand it. So I will begin with where I left, but there will be some gaps, because what is the form of Christoffel symbol that I will derive tomorrow. But because I am in a hurry to make a connection with curvature tensor, so I'll fill in the blanks tomorrow. So we figured out yesterday that for any vector field V mu, vector field V mu of x, the covariant derivative with respect to alpha is ordinary partial derivative that we derived yesterday, plus there were some things called Christoffel symbol, we don't even know how they look like. Okay. And nu is repeating, so it's being summed over. We still don't know how gamma mu nu alpha, what they are given by. Okay. Similarly, we prove that if you have a covariant vector field, then let's call it mu, then its covariant derivative with respect to alpha is ordinary partial derivative u mu of alpha. Remember, comma alpha is ordinary partial derivative with respect to x alpha, then minus gamma alpha u nu, and because it is mu. Yeah. Then I told you that if you want to know what is the covariant derivative on mixed tensors, you can take them to be appropriate product of contravariant vector and covariant vectors, and derivatives are they essentially have the Leibniz rule. From that you can derive. What I mean is that supposing you want to talk about a mixed tensor T mu nu, and you want to write what is its covariant derivative. Okay, I will first give you the result. I will tell you how to derive it. So this you can show is T mu nu, ordinary partial derivative alpha. There is a contravariant index that will be like this, so therefore will be gamma mu with respect to alpha, nu. Oh, nu, there is also nu, so I better not use the index nu, sigma nu. But this nu is a covariant index. This will be like this, so minus gamma T, now mu, sigma, the derivative with respect to alpha, and there's a nu. Okay, it will be for a mixed tensor, this will be covariant. How will you derive that? Very easy. What you do is, after all, a tensor v mu into u nu is a tensor of this kind. Find out what is its covariant derivative and use Leibniz rule, because this is same as v mu semicolon alpha u nu plus v mu u nu semicolon. And this you know how to do it. V mu semicolon alpha you know, u nu semicolon alpha you know. You do it and you will find a general mixed tensor can be written in this manner. Similarly, if you had a covariant tensor b mu nu, then its covariant derivative alpha will be similarly partial derivative, ordinary partial derivative. Now there will be two minuses because they are all covariant indices. So alpha mu sigma nu, then nu alpha mu sigma. So you don't even have to remember, because the upper index will be like this, lower index will be like this. And a general second rank contravariant vector field will be A. Okay. Yeah, for the completeness, I have given you this relations. All this can be derived purely from these two. You don't need anything else. Now, because I don't have time, I will only give you the result. It is very easy to prove it. Okay. Prove that if you have a vector field V mu, okay, take a vector field V mu. First, take its covariant derivative with respect to beta. Then you take covariant derivative with respect to alpha. Then from that you subtract V mu take covariant derivative to alpha, covariant derivative to beta. Yes, it will be algebraically very complicated because you are taking covariant derivative twice. You will find that, by the way, this is a proper tensor because we are using covariant derivative. Covariant derivative ensures that you are using tensors all the time. This is a tensor, proper tensor, this is a tensor, this is a tensor. That is what covariant derivative assures. Just like in the gauge covariant derivative, TP has said that if you have a gauge field psi or any field, so that under a gauge transformation it goes to e raised to power phi psi, where phi, the angle phi depends upon space, then ordinary partial derivative del mu psi is not e raised to power I phi del mu psi, but gauge covariant derivative does that. So in a sense, arbitrary coordinate transformation and gauge transformation, they have a similar thing. So the phi sits in the fiber. Psi is the base field. The e raised to a phi psi, those are in the fiber. So I am just making a connection with gauge field. This object is a tensor, and therefore whatever will be there in the right hand side will be a tensor, and you can show that it is a tensor. Let's call it R mu. It will be proportional to R mu. I have alpha beta, so therefore I'll have nu alpha beta v nu. I have written proportionality. What I mean is it will be either plus 1 or minus 1. I'm forgetting, so that's why I'm not writing. It will be, when you do the calculation, it will be either plus 1 or minus 1. And what is this quantity? What is this tensor R mu nu alpha beta? It will turn out that R mu nu alpha beta is related to derivatives of the Christoffel symbol gammas. Now let me fill in the indexes. Mu nu, it will be first mu and nu. If it is alpha first, derivatives alpha here, beta here, and be antisymmetric. So mu nu, it will be beta alpha, then I'll put mu mu, nu nu, and sigma sigma, sigma sigma. It is alpha first, alpha beta, is beta alpha. So this object, it's a tensor, it better be a tensor, because if you have a relation where you have tensors on the left side, the right side better be tensor, because so that they transform appropriately under arbitrary coordinate transformation. So this result itself, when you do the calculation, will tell you whatever you have got as R mu nu must be a tensor. That means the other way of saying it, you don't have to prove additionally that this object, this partial derivative and product is a tensor. By the fact that it is equal to this is a tensorial relation. Okay. That's the first thing. And you have encountered this object even before when Bhashwati talked about a geodesic deviation equation, that you indeed derived a relation So you indeed had derived a relation that capital D, remember D is the actual separation, D square by of D separation between two geodesic delta x mu by D lambda square, where lambda is labeling the geodesic. You could have taken the proper time also, proper distance, doesn't matter, it's proportional to R mu nu alpha beta. I mean, again, plus minus, I don't remember plus minus, so you'll find u nu u alpha, where u's are the 4 velocities of the geodesic, and delta x beta. So there will be plus minus, that's why I'm writing it as proportional. And this is the geodesic deviation equation, which tells me that if this is a geodesic whose 4 velocity is u, this is another geodesic with 4 velocity, they are separated by 2 amount, and the separation is delta x mu. Then this separation evolves as you freely fall according to this equation. And this is exactly the Riemann curvature tensor. You can very easily, by the way, okay, pause. I have to tell you about local inertial frame also, because that will also tell me how to simplify things. Now, what is a local inertial frame? I have only given one, what is a local inertial frame? Yes, local inertial frame is a frame, so is a freely falling frame. It's such a frame that yes, you can set up a Minkowskian coordinate system inside, so that inside the metric is eta alpha beta, your Minkowskian coordinate system is zeta alpha beta, which from the point of view of curvilinear coordinate system, so what you have done is that you have chosen such a coordinate system that at one point within the local inertial frame, call that point, let's say x0, your Christoffel symbol in the local coordinate system, mu alpha beta at x0 is identically, this x0 is not 0, okay, let me call it xp, point p, xp. The Christoffel symbol at this point is 0, and so that to first order in the separation, the metric here is eta mu nu for at every x, such that x minus xp modulus is much less than some value. Okay. So within a local inertial frame, everywhere to first order in the separation, it is metric tensor is eta mu nu, but at one point the Christoffel symbol is 0. Only at one point. It can't be 0 everywhere else, because Riemann curvature tensor is a proper tensor. That will not be 0, and therefore the derivative, these derivatives will not be 0. Okay. Now, there are various symmetry and antisymmetry properties of the Riemann tensor. How to figure out? The best way, this is, Landau had this smart way of getting at results by simple argument. Supposing I want to know all the symmetry and antisymmetry properties of this tensor. A tensor's properties will remain invariant in whichever frame you go to. It doesn't matter which frame you are looking at it. So Landau-Lifshitz will tell you, very good, you go to a local inertial frame. If you go to a local inertial frame and you are at this point, the Christoffel symbols go to 0. So at the point P in the local inertial frame, at xp, in the local inertial frame, in your local inertial coordinates, only these two terms will be there. And it's a tensor. So you're at xp in a local inertial coordinate system, your Riemann curvature tensor at point P, at xp, is just del gamma mu nu beta by del x alpha minus del gamma mu nu alpha by del x beta. The other terms are 0 because you are only calculating at xp. Okay. Very easy. So what are the antisymmetry symmetry properties? You can immediately see that r mu nu alpha beta r mu nu alpha beta is simply minus r mu nu beta alpha. Okay. Okay. Then the other property you can easily prove, I'll give it to you as an exercise, that this object nu alpha beta plus cyclic rotation beta nu alpha plus r mu alpha beta nu is 0. Okay. Now you can also construct another quantity, because you can lower and raise. We have talked about lowering and raising using the metric tensor. You can construct, you can lower this in the upper index to below by using the metric. So G mu sigma R sigma nu alpha beta. This is by definition. You have lowered the upper index using the metric tensor, and you can prove that there are other properties. Where am I writing the properties? Yeah, here. You can prove that R mu nu alpha beta is same as R alpha beta mu nu. And similarly, R mu nu alpha beta is minus R nu mu alpha beta. These are the various properties you can very easily prove using this form. That means you go into a local inertial frame and look at that point xp where the crystal symbol is 0, and you can prove all these properties in a very simplified manner. Okay. So I will stop here, except I will tell you how to calculate these quantities. By the way, calculation of these quantities, there's a trick to calculate these objects. You could have done it in local inertial frame. That's a simpler way of doing it. But there's a way. First you take out the outer derivative, because outer derivative you know for a tensor. If you first take the inner derivative, you don't know how to do the covariant derivative. Because covariant derivative or ordinary partial derivative is not meaningless. So first take out the outer derivative and then take out the inner derivative. Then you can show this. Okay. So do all these problems so that I'm sure you would have done it at some level, so that the tensor calculus you become very comfortable. Incidentally, you can probably, just like this trick, this is a tensorial equation. You could have done everything in the point xp in a local inertial frame. That would be much simpler. Okay. So I'll stop here, and if there are any questions, then you can ask. Yeah. No question is silly.
So we lower the index for R. Does it matter if we put the index on the left hand side or left side or right side of the?
Say that again. So remember the position. When I have written sigma, these have been displaced. That's very important. I must tell you, very often a beginner person gets confused about one thing. If I have a tensor, mixed tensor mu, the lower index, I better write it like this, because this is in general not same as A nu mu. Remember the separation. This is very important. These are in general not same. Only if A mu nu downstairs is A nu mu downstairs, only then they are, it doesn't matter. So there is a separation. So therefore, if I lower this index, so A mu nu, I can lower it by using G mu sigma A sigma nu. Nu is separate. So I am lowering the first index. Okay. Supposing I had a object like this, then if I put G mu sigma A mu nu, it would be, mu has been lowered, it will be A sigma nu. But I could have lowered nu also. If I do that, G nu sigma A mu sigma, it will be A mu nu. These two things are different. So it's not silly question, very important to know where you have placed the indices. Otherwise you'll make errors. Okay? I hope I have cleared the, yeah.
If we take a coordinate system, will this affect how we write? If we take some particular coordinate system?
No, because tensor by themselves, their properties, their invariant properties like symmetry, antisymmetry, they don't depend upon which coordinate system you have chosen.
But if sigma mu you are interchange here,
Huh.
writing.
No, so this being not equal to this in general, it doesn't depend upon coordinate system. But that's obvious. I have not chosen any coordinate system here, right? These tensor identities are independent of coordinate system. Yeah? Yeah, but these are very important because when you are doing calculation, unless you pay attention, you will make errors. And by the way, let me tell you, many published papers, the authors have not been careful and they have made mistake. So their results, you cannot trust them. This is very important.
So in a coordinate, like if you have like big expansion of R, you want
Say that again?
this Riemann tensor
Yeah.
R, if you have such a big expansion and you
It is. This is the definition of Riemann tensor. Yeah.
But according to you, there is a coordinate transformation which
Yeah.
can reduce.
Supposing you want to do simplification, because I know that in Einstein's general relativity, I have the freedom to choose local inertial coordinate system, and
Such a transformation.
what?
What will be such a transformation that can reduce to this simple form?
Yeah. So that was one of the problem right in the beginning we circulated, that how do you actually construct a local inertial frame, and we had given some. The basic concept is what? That you're making a coordinate, earlier coordinate system is x mu. In this coordinate system, metric tensor is this. I want a coordinate system where in a small region metric tensor becomes eta alpha beta, right? That is what is a local. So therefore, I make a coordinate system x mu going to xi alpha, okay, and so that this equation is satisfied. Eta alpha beta is equal to so I have to choose xi alphas. Given x's, I have to choose xi alpha and set up this differential equation. Or you can do the invert. In the invert thing, you'll have g, the equation is g mu nu of x is del x, no, eta alpha beta upstairs is del xi alpha by del x mu, del xi beta by del x nu into g mu nu. So in your curvilinear coordinate system, you know g mu nu upstairs x, you want those xi alpha. So you have to solve this equation. And this is not enough. You have to put that at one given point, the Christoffel symbol in the new coordinate system is 0. Oh, by the way, I had asked you to find out the transformation property of the Christoffel symbol. I hope you have done it. Very important. I will list that transformation property because this is where how to get the inertial coordinate system, very important. So let me give you the result. I had asked you to prove it. So when you have gamma mu alpha beta. When you make a coordinate transformation, x going to x prime, then in this new coordinates, your crystallizable symbols are gamma prime mu alpha beta at x prime, where x prime, this event, same event in the new coordinates of x prime, in the old coordinates of x, this you can prove is nothing but del x prime mu by del x sigma. Then I'll put in the index soon. Gamma sigma lambda tau, so that lambda tau, this is alpha beta. Now, prime alpha beta lambda tau, plus there is an additional term, and that is what makes it so had this term not been there, then your crystallizable symbol would have transformed like a tensor. But the fact is, there is this term. That tells me that crystallizable symbol is not a tensor. So when you make a transformation, at one point you have to say that it is 0. And that's how he will get the local inertial coordinate system. Note from the transformation properties of the crystallizable symbol, note that I have not yet proved whether gamma mu alpha beta is same as gamma mu beta alpha. Is the crystallizable symbol symmetric in the index alpha beta? I have not yet told you anything about it, but you can prove from the transformation property that gamma mu alpha beta minus gamma mu beta alpha is a tensor. Although gamma mu alpha beta by itself is not a tensor because there is an additional term here, but this is a tensor. Why? Because when you subtract out and do the transformation, this term cancels because partial derivatives commute. So it's obvious that gamma mu alpha beta minus gamma mu beta alpha is 0.
Only if torsion is absent.
No, wait, I have not even introduced torsion. All I am saying is that gamma mu alpha beta is not a tensor because when you do the transformation, there is an extra piece. Now I will say, okay, let me construct this object gamma mu alpha beta minus gamma mu beta alpha and ask what is this transformation. When I do the transformation, I will find gamma prime mu alpha beta minus gamma prime mu beta alpha. There will be this minus that, but this term will cancel because partial derivatives commute. So this object is a tensor. And what is that tensor? Those people who want to introduce a torsion in their theory, the torsion is precisely S mu alpha beta is defined to be gamma mu alpha beta minus gamma mu beta alpha. In Einstein's general relativity, torsion is set to 0 so that the crystallizable symbol is symmetric. We'll come to that in the next lecture. Today I thought I better do the Riemann tensor so that there's a continuity with tomorrow's lecture by TP because he is going to talk about torsion, talk about Riemann tensor from the differential geometry language. Okay? Yeah, Anuj.
So the fact that we can set up a local inertial frame up to first order in metric derivative.
Yes.
Should I cover this problem in the review?
Yes, because if you can do it, it will be wonderful.
But we cannot set it to 0 with the second derivatives.
Correct. Absolutely. Yeah, that will be wonderful. So I hope you are getting what Anuj is saying. Up to first derivative with the metric tensor, it is 0. But the second derivative of the metric is no longer 0 in the local inertial frame. Why? Because Riemann tensor is a tensor. That can't be 0 in the local inertial frame. Later on, I'll connect the Riemann tensor with tidal forces. It is connected with the tidal force. Yeah, that will be wonderful actually. Yeah.
Doubt on that. The first derivative is 0 at a point x is correct. You can choose a local initial coordinate like that.
First derivative of what is 0? The metric tensor, yes. Yeah, that's what is a local inertial.
Not always 0.
Huh?
Second derivative.
Yeah, you can show that you can't make the second derivative 0 at a point.
So what will be the natural point P?
No, you can choose. That is your origin. You can choose your origin anywhere inside this small local inertial frame. That's your origin.
No, what I mean is there will maybe a maximum, minimum, or saddle point. We can get information from that.
That depends upon the detailed geometry, whether it is a saddle point, whether it is something is maximized or minimized. It depends on the nature of the metric, how the metric behaves in that small region. All right, so yeah, there's a question.
So does the index spacing not matter when it comes to the Christoffel symbols, because the mu is written right above the alpha?
So remember, the Christoffel symbol is not a tensor. Gamma mu alpha beta is not a tensor. But when you try to subtract it, this is a proper tensor. When this is a proper tensor, you better tell me exactly where the index spacing is. So the torsion tensor S mu, you have a proper separation that this mu is upstairs, alpha beta is displaced, and this will be written as gamma mu alpha beta minus gamma mu beta alpha. So when you are constructing a tensor using the Christoffel symbol, then you have to be very careful about the spacing, because if you are dealing with torsion, you know that when you lower it, you get S mu alpha beta. When you raise it again, you can raise it either to this, but you could have raised alpha beta, where alpha being raised, this alpha is from the middle, it has been raised. This is not same as this is not same as this. So you have to be very, very careful. So people who work with torsion, they better be very, very careful, otherwise you'll get results, you might feel that you have got a non-trivial result, but it may be a mistake because you were not paying attention to how you are raising the indices.
I've seen some books which talk about these Christoffel symbols of the first and the second kind.
Yeah, I will talk about it because I'll talk about it in the next lecture. Yeah.
So the mu where exactly?
Where, yeah. But at the same time, we must realize Christoffel symbols by themselves are not tensors. Because they can be 0 in one frame, in local inertial frame, at one point it is 0, but in another coordinate system they are not 0. So they cannot be tensor. That was one of the problems we had circulated earlier. A tensor, if it is 0 at an event in one coordinate system, in all coordinate system it has to be 0 at that event. That is guaranteed by the transformation properties of the tensor. So that itself tells you that Christoffel symbol cannot be tensor. Physics, what is the physics? Christoffel symbols are the fictitious forces. With the inertial frame, there is no fictitious force. In accelerated frame, fictitious force. So Christoffel symbols should be identified with the fictitious forces, while Riemann tensor should be identified with the actual tidal forces. So there is the physical connection between what is a Christoffel symbol. For a regular observer, you see fictitious force, you will find Christoffel symbol is non-zero.
So when I interchange the symbols in the Christoffel symbol, that becomes a tensor, and that
No. Wait. Christoffel symbol itself by itself is not a tensor. So therefore, by all this you can prove gamma mu alpha beta minus gamma mu beta alpha is a tensor.
And that arises
But in standard general relativity, this tensor is identically 0
torsion.
in a standard general relativity. But people who deal with torsion, because today I asked TP what did he do? He did Cartan's first equation. There you had torsion. If you assume that the torsion is non-zero, then it will be gamma mu alpha beta minus gamma mu beta alpha beta will not be 0. Rather, it will be the torsion tensor.
So the optionless case, we can put the mu anywhere in the bottom. You lower the bias. In the torsionless case, for crystal symbol, can
No.
we put the low?
No. Anyway, it's not a tensor. No? What do you mean by raising and lowering? But as you were saying about Christopher symbol of first kind, it's a definition. I'll tell you what it means.